is on the board behind me. And so let's give a warm AAA welcome to Jillian Bellovary.
All right, thank you everybody for coming. What a great audience. It's great to see everybody. Thank you for the introduction, David. Makes me sound very important. So tonight we're going to talk about gravitational waves. And I chose this topic because it is awesome and I love it and I care about it, but also because it's been in the news recently, within the past almost a year or so now. And people are like, what the heck is a gravitational wave? And it's actually not that hard to explain if you put a little bit of effort into it. And so that's what I want to do today. I want to help you understand gravitational waves. So when you hear more news in the future about it, you'll be like, I remember that. That lady in the purple dress with all the equations on it told me about that thing. So here we go. Gravitational waves, ripples in space. So before we answer what the heck is a gravitational wave, let's answer this question, what the heck is space-time? So mathematically, it turns out space and time are kind of the same thing, but to us, we're just like, what? What do you mean it's the same thing? It doesn't make any sense. So let's think about an analogy. Think about space-time as a rubber sheet. And if you have something massive that you put on the rubber sheet, it's going to bend the rubber sheet. Do I have a pointing thing? Anyone? Do I have a pointing thing? All right, the AV guys get me one. Cool. Otherwise, I can just walk up here. So if you put something medium-sized, like the sun, which is totally not medium-sized, but whatever, on a rubber sheet, it's going to put a dent in the rubber sheet. Something heavier, like a neutron star, is going to put a bigger dent in your rubber sheet, which is going to curve space-time. Space and time around this object are bending. The black hole bends space-time the most because you have the most amount of stuff, of matter, in the tiniest space. And so space and time will curve and bend around these massive objects. So mass bends time and space. Like it's a rubber sheet. Except the rubber sheet is in 2 dimensions, we hang out in 3 dimensions, so it's a little different. It's a good analogy. So ripples in space-time are kind of like water droplets in a puddle, right? You can see as the water droplet goes up and down, the waves propagate through the water. And so if you can think about ripples in space-time, they kind of do this, but to space. Space wiggles. So when a gravitational wave goes through you, it squishes space in one direction and stretches it in the other. So, for example, what's your name, sir?
William.
This is William. William and I are standing like 1 meter apart-ish. I can't get any closer because I'll fall off. We're about 1 meter apart. If a gravitational wave comes through us, it's not that we'll move back and forth like this, because we won't. We'll both be where we are. But space is going to expand and contract. And so if we are 1 meter apart and holding a meter stick, the meter stick will stretch and squish and stretch and squish. So it's like the length of a meter is changing. But it's still a meter getting longer and a meter getting shorter. Thank you. Actually, so space stretches when gravitational waves pass through. So I don't really know what we would feel. People are like, what would you feel if a gravitational wave went through you? It would totally feel weird, I think, but I can't really describe it aside from that. It would be weird. Then feel your body stretched and squished. So we would be stretched in one way and like squished in the other. So I have a little movie here, which is an exaggeration of what would happen if a gravitational wave went through the Earth. So the gravitational wave is sort of represented here by like some green waves that are passing through. And you can see how Earth is stretching and squishing and stretching and squishing. That's what it would be like to experience a gravitational wave if it were magnified by a gazillion times. So that will never actually happen, but you kind of get the idea of what it does to space when it passes. So, what types of things emit gravitational waves? A couple different things. Black holes, when they're orbiting each other and when they merge, will emit gravitational waves. A black hole and a neutron star orbiting each other and eventually merging will also emit gravitational waves. Two neutron stars will do that too. They emit gravitational waves as they orbit and as they merge. What else? Supernova will also emit gravitational waves. In the supernova explosion, you form a neutron star or a black hole, and the formation process there will make gravitational waves. It will cause space-time to ripple and shift. The Big Bang will produced gravitational waves. A few years ago, people thought they detected this, but it turns out they were wrong, and they didn't. Gravitational waves from this. But maybe we still will. So the Big Bang was basically the most exciting cosmic event that has ever happened because it made the universe. So it also will produce gravitational waves. Big gravitational events produce gravitational waves. Also, question marks produce gravitational waves. What does that mean? It means stuff that we probably haven't thought of will also produce gravitational waves. And that's why it's so important to learn to detect them. So we can figure out what is the other stuff that we haven't even thought of yet that is going to make gravitational waves. So right now it's question marks, but I'll fill it in with a cartoon of some cute thing as soon as we discover what that is. So how do we observe them? We can't feel them. I showed a cartoon of them rippling through the earth, but really the effect is very, very small. Not something we can feel. We can't use a ruler because our ruler will stretch and shrink along with the gravitational waves. So that's not going to help. If our ruler changes along with the waves, we can't use it to measure anything. We definitely can't use a telescope. There's no light involved at all. So telescope, not helpful. So we need to build a machine that feels the ripples in space-time. But here's a hint. Light is impervious to changes in space-time. The speed of light is constant. It is always the same. So we can use this fact that the speed of light is always the same to build our device that will detect these things. So when in doubt, use lasers. Lasers are so cool. I have one in my hand. Ta-da! Lasers. Lasers, and in particular, a property of light called interference. So if you have two waves of light that are lined up so that the peaks and the troughs match each other, when you add them together, it creates a bigger wave. This is called constructive interference. You're constructing a bigger wave. However, if they're not lined up, if they're opposite, so the peak and the trough and the peak are lined up together, when you add them, they cancel each other out. You get nothing. It's called destructive interference. You're destroying your wave. And this property of waves will be really important in how we detect gravitational waves. So we're going to build something called an interferometer. It's not an interferometer, it's an interferometer. It sounds better that way. And what we're going to build is a really huge interferometer, something called LIGO. So how does an interferometer work? What is it? Well, there's a laser here, an all-important laser. There's a whole bunch of mirrors, and what happens is that the light goes either through this mirror and bounces off, or it reflects and goes up to this mirror and bounces off. And both waves will come down here into this light detector. And when you have two different waves that are coming together, they will either interfere destructively and make no wave at all, or interfere constructively, where they add together and make a bigger wave, or somewhere in between. And you can adjust your interferometer to make different interference patterns. So what we want to do is build a giant one of these and call it LIGO. LIGO is the Laser Interferometer Gravitational Wave Observatory. There are actually two LIGOs. There is one in Hanford, Washington, and one in Livingston, Louisiana. These are huge. This is 2.5 miles long. So this is a really, really big interferometer. And so why are there two of them? Well, if we could build a ton of them, we would build a ton of them. But there are two of them because we're trying to measure gravitational waves that pass through the Earth from space. But there are a lot of things that can interfere with that. For example, earthquakes. Those are no good. They act like a gravitational wave. Even planes flying overhead can make these really sensitive detectors feel something. The waves from the ocean coming up onto the shore also. But if we make more than one of them, we can erase these effects. Because if an airplane flies over Washington, it's not going to fly over Louisiana. If an earthquake in Louisiana, it will feel different in Washington if you feel it at all. And secondly, we can help figure out where the wave came from. We have many detectors. So that's why there are two. I'll tell you later about how there may be more. But let's talk first about how it works. So I have a little video here of how the interferometer works. It follows this laser. And instead of having just mirrors here, there's actually a little bit of a mass here on this mirror, which is going to look like this, which I'll tell you about in a second. Let me play the movie. Okay, so there's your laser. That's what it looks like when it happens. And when these masses wiggle back and forth, that's when a gravitational wave passes through them. The gravitational wave works space-time so that those masses wiggle. So here we're following the laser. As it hits the mirror, reflects back, rejoins the other wave, and gets to the detector. All right, so now a gravitational wave is going to come by, and these masses are both going to move back and forth, stretching in one direction and squishing in the other. You can see how that changes the way that the light, two rays of light are lined up. And it changes the pattern that you see on the detector. And so it's because of the way this pattern changes that we can detect the gravitational waves when they go by. We see those masses, they wiggle when the gravitational wave goes by. We see this pattern shift. We say, hey, I think I got something. Did the other detectors see it? Hey, maybe we did get something. They saw it too. Then we run all our analysis and try and figure it out. So what is on these detectors, on these masses? Well, in order to be so sensitive to detect a really, really small wiggle, you have to do a lot of different things to make sure that you don't catch seismic events or other things. One of these LIGO detectors actually had a truck drive into the tube of it, which probably made it look like a fake detection because it was hit by a truck. I think everyone was okay. They definitely wrecked the truck. And so what's on these detectors, there's a thing, well, sorry, here's the test mass. This is what the laser hits. And in order to prevent it from being shaken by events on the Earth, you hang it from a pendulum from another thing. But this pendulum is hanging from another thing, which is hanging from another thing. So you basically have this intricate array of pendulums all together that will prevent regular seismic events and other earthly events from looking like a false detection. And how precise does it have to be? It needs to be so precise that if we were measuring the distance to the nearest star, it would have to be accurate to the width of a human hair. That is how precise it is, because that is how small the movement is. The actual measurement is a fraction of the diameter of a proton. We measure something that small with a laser and the Gravitational Wave Observatory. So we need to decrease the noise in the background sources by a lot. So we do that by having an intricate source of pendulums. We super cool it The tubes are a vacuum. And all these things together make it be so accurate that we can detect something, a fraction of the diameter of a proton. Protons are really small, guys. This is really small. This is amazing. This is amazing. So the history of gravitational waves, they were thought of by Einstein 100 years ago, in 1916. And in the 60s, some people thought of the idea of LIGO. They were like, maybe we can use an interferometer. Because lasers had like just been discovered, and like, maybe we can figure this out. And then in the 90s, people finally convinced the government to give them money to build one. Because the idea was now good enough that you could convince other people to let you do it, and to give you money. And so LIGO itself, it was finished being built in like the early 2000s, and it didn't work. It detected nothing. Everyone was like, oh crap. We just spent millions of dollars and we detected nothing. And people were like, but no, wait. If you look at what we predict and what we've got here, we just need to make it more sensitive. We need to make it better. We're almost there. We're so close. Please, government, give us more money. We promise. I don't know how many people ask the government that and get what they want, but the scientists did. And so they upgraded it. And in 2015, it went live again. And they're like, okay, now for real, we will get the gravity. For real, we're going to do it. And like 3 days after they turn it on, they detected gravitational waves. So a gravitational wave detection of merging black holes looks like this squiggly line. So what is this squiggly line? It's time is going this way. And this is the amount of wiggle of the detector, of that mass that's wiggling back and forth. It's how much it's wiggling back and forth. So when the gravitational wave comes by, as these black holes merge, it's kind of noisy, and then it's like, okay, all right, oh, we're merging, and then, we merged. So the red one is the Washington LIGO, and then the blue one on top of it is the Louisiana one. So they agree. And if you make a model of what the signal from two merging black holes should look like, it looks beautifully just like the detection. Beautifully. So this was amazing. We're like, yes, we finally did it. This is real. And what I have here is a movie of it that's kind of translated into sound. Because it turns out that the frequency of the oscillations of the gravitational waves are actually within the frequency that we can hear. We can't hear them, of course. They're not a sound wave. They're gravitational waves. But if we convert it into sound, we can make it like something that we can hear. So I haven't tested the sound. Let's make sure this works. AV guy, paying attention. This doesn't work. I need your help. Okay. Okay, so what the heck was that? I'll play it again. So what's here, this squiggle is the same squiggle as before. This is the signal of the detector shifting. What's here is the frequency this is time again. As the black holes get closer and closer together, the frequency increases. So there's this curve upwards. These are the two detectors. So the first lower sound that you hear is the real frequency. That's the real frequency of the merger. But it's kind of a weird frequency. Like we can hear it, you can hear it, but it's very weird sounding. So then they increased the frequency of it, increased the pitch so that it was easier to hear. And so it first played at the real frequency, and then the higher one, and then the low real one again, and then the higher one. So let me play it again now that you know what the heck I'm talking about. So that's really fast. Like all of the stuff that I've been talking about for like less than 1 second of detection. But in that 1 second, we have enough information to know that two black holes have merged. So here's another movie that has translated this data into colored space-time. So regular, flat, boring space-time is blue. And the two black holes are the black circles that are hovering above our space-time. So the space-time here is this two-dimensional color thing. And then the space-time bending of near the black holes is these colored rainbow pits. And so the black holes are getting closer and closer together. And as they do that, space and time are warping around them. And so as the black holes are finally about to reach each other, weird stuff's going to happen. The movie will freeze so you can look at it better. They're merging right here. They've merged. And now that they've merged, space-time ripples and becomes normal again. The people who made that movie. I didn't make that movie. Movies on the internet. So, let's hear about this merger. What's going on? What are these black holes all about? These two black holes had masses of 36 and 29 times the mass of the sun. This symbol here means the mass of the sun. So they're pretty big, bigger than the sun. The final mass of the merged black hole is 62 times the mass of the sun. You might notice, if you're quick at math, that 36 plus 29 does not equal 62. What happened? 4.6% of the energy, so about 3 solar masses, is what radiated away in gravitational waves. So some of the mass was converted to this gravitational energy and radiated away. So that's what we're seeing, the gravitational waves. This merger happened 1.3 billion years ago. Okay? It happened in a very distant part of the universe. Pretty distant anyway. There are more distant places, but it's far away. I don't think we actually knew that LIGO would be able to see that far away. But then we're like, oh, sure enough, we can see it far away. We confirmed that the speed of light and the speed of gravity are equal, which we thought was probably true, but now we know. And this detection was really, really strong. There's something called the signal-to-noise ratio of 24, which is really high. This is a really strong detection. This is not a mistake. This is not some earthquake or some other weird phenomenon. This is totally detection of black holes merging. There's no other way to explain it. So this happened in September in 2015. There's another one that happened a few months after that, on Boxing Day, the day after Christmas, that same year. This one had smaller masses, 8 and 14 times the mass of the sun. But this one is cool because we observed 27 orbits of the in-spiral before the merger. So we saw the black holes go around each other 27 times, which lasted an entire second, a whole second, as opposed to like the 0.3 seconds of the last one. So the black holes are smaller. This one is also really distant, and we know that one of the black holes was spinning based on our models. But this one doesn't have the great big signal the other one has, like those big wiggles that you saw. The wiggles look like this in this one. They look like a mess. They look like somebody stepped on the detector. But apparently, with a lot of statistical and mathematical power, you can get a detection out of that. So you might wonder, where in the sky are these things? Where did they come from? So with only 2 detectors, it's really hard to tell. Here's a map of the sky in a sphere. And the first one, we know happened in like a blob that covers about a quarter of the sky. And the second one happened in an area that stretches across like half the sky. But it's a skinny area. So we totally don't know where they came from. I can be like, sort of over there. And you'll be like, well, where do I point my telescope to see anything? And I'm just like, I can't help you. With only 2 detectors, it's hard to tell. But we're going to be building more. And so this is a problem that will be solved in the future. But with only 2, it's tough. You can see Basically, whichever detector gets it first, you know it's kind of that way. So if Washington gets it first, you're like, all right, the direction is Washington-ish. Louisiana gets it first, it's Louisiana-ish. But that's kind of all you got. But there will be more, and we will solve this problem. In fact, there are rumors that more have been detected. But LIGO scientists are sworn not to talk about it. And the LIGO scientists I know who are sworn not to talk about it are like, yeah, there's more, but I can't talk about it. So stay tuned, because you are now an expert in gravitational waves. So when your friends are like, did you hear about those gravity wave things? You can be like, I know about that. Let me tell you. So you've got a lot of background info now. Let me tell you why I care. What do I, as a scientist, care about this? Besides the fact that it's awesome. It's not enough for people to give me money to do my job, just to think it's awesome. Otherwise, we could all be great astronomers. So there's a mystery about this first detection, especially. These black holes that are 36 and 29 times the mass of the sun, they're weird. These black holes are big. We do not expect them to be this big. Stellar evolution models predict a maximum mass of like 20 times the mass of the sun. And those that are 20 are really, really rare. They're not supposed to be a lot. They're just supposed to be a few. One here, one there. Most of them are more like 5 to 15 times the mass of the sun. 36 and 29 are really big, weirdly big. So how do you get not just one, but two? And then you get them to be in the same place, and you get them to orbit each other in such a way that they merge. This was not expected. Our regular ideas for how stellar evolution works and how black holes form do not predict anything like this at all. So right after we're like, yay, gravitational wave, people are like, what? What? Why? How? Who? Eh. Pretty much what we said. We all sat around and being like, yeah. So we need to think of a new mechanism for forming black holes that can make sense of this, that can explain how you get two big black holes together. So some collaborators and I have an idea. So I'm going to divert us for a little bit, and we're going to talk about planets. Sorry, put the black hole over here. Planets. Why do we care about planets? Well, we only kind of do, but this is important. So here we go. Planets, we think, form in a disk around a star. Here's our star, here's our disk, there's some little planets there, and they're built by a buildup of planetesimals, basically little planety pieces that come and smash into other planety pieces and little bigger planets. That's how we think that happens. These planetesimals migrate in the disk. They move outward and inwards because the disk basically kind of torques them around. The disk is like, hey, there's a lot of force this way, you should move out. And the disk over here is like, no, the forces are this way, you gotta move in. So these planetesimals are moving in and out all around, depending on the torques in the disk. And it turns out that there are some sweet spots where the torques balance. This torque pushing out and this torque pushing in, they have to meet somewhere. And where you meet in the middle, you end up getting stuff piling up. And so when you get stuff piling up, it can merge together. So people think this is pretty important for forming planets. You want to form planets fast. And so this is one way to do it. If you have a place in the disk where all the forces are balancing out, you can get a bunch of stuff that piles up there, sticks together, makes planets. Okay? Okay, done with planets. Oh, these sweet spots are called migration traps because they're migrating and they get trapped. Migration traps. Okay, no more planets. Back to black holes and migration traps. So, a similar situation, but like a gazillion times more massive, is a supermassive black hole in the center of a galaxy. A supermassive black hole often also has a disk around it. That disk is called an accretion disk. And that disk is full of gas that's usually accreting onto and feeding the black hole. So it's a similar situation. We have a heavy thing, with a disk around it. So supermassive black holes have disks around them, and there are stellar mass black holes, little regular black holes like the ones that form from dying stars, in this disk, because there are stars forming in this disk. So you're going to get a bunch of little black holes in the disk that are like the planetesimals. They're doing the same kind of thing, which means that these black holes can migrate in the disk. They can move outward, they can move inward, and in the places where the torques are balanced, they can pile up in the same spot. And when they pile up, they can merge with each other in these migration tracks. They can also get bigger because this disk is full of gas, and black holes love to eat gas. Gas is delicious to a black hole. Black hole is all about eating this gas. So the black hole can grow by eating the gas, and it can grow by merging with other black holes. And so what I think the result can be is that if you get lots of black hole growth through these mergers and through this gas eating, you can make bigger and bigger black holes. So I think my explanation for this first gravitational wave detection of these overmassive black holes is that these black holes live in the accretion disk of a supermassive black hole. These black holes are migrating in this disk, chomping up gas, and merging with other black holes so that they can get extra big. And because they get extra big, they can make an event like we detected with LIGO in a way that makes sense and doesn't break our other ideas of stellar evolutionary theory. So am I right? I don't know. So I've done some math, and I've figured out that migration traps probably do exist in these disks. My next step is to run computer simulations of this process. So I'm going to run some simulations of black holes in a disk, see if I put a bunch of black holes in, what they do, maybe send them in different directions. Some will go this way, some will do that way. See how fast they grow, how often they merge, and can we reproduce the kind of signal that we saw with LIGO? And how many more will we see? How many more will there be? If any of you are a student wanting a research project, you should come talk to me. So I need some help here. So this is what I, as a scientist, care about. This is what I am thinking about right now. So what is the future of gravitational wave detection? We have these two guys right here who are working. And this one kind of doesn't count because it doesn't really do anything. This green one, Virgo, is in Italy. And it is going to go online this summer. And so then there will be three. Virgo is identical to these other two. Like it has the same engineering, the same design. So then there will be three. That will help a lot with figuring out what direction things came from and just sensitivity in general. There's one that's being built in Japan, and the Indian government recently put money forth to building one there. So there are going to be an array of these all around the planet. LIGO is also constantly being upgraded. It's been out of service for several months, actually, because they're upgrading it again. Like, didn't we just do that? I thought we fixed it. But no, we're going to detect better and more things with this new upgrade. They actually turned it on again for science on Wednesday. Like 2 days ago Wednesday. So any day now, there might be another detection. Excuse me. So that's cool. Well, what else? The biggest plan is to put one in space. Put an interferometer in space. ELISA is the Extended Laser Interferometer Space Array? I don't think that's right. I think space is not right. I'm not sure what it means. But it's an interferometer in space. So to detect supermassive black holes, the huge ones that are in the centers of galaxies, we can't actually detect those merging with LIGO. The frequencies are wrong. We would need to make LIGO way bigger than the Earth, in fact, in order to detect them. So what do we plan? We plan to make a detector bigger than the Earth. This is 3 free-floating pods in space that will make an interferometer. This is, so the Earth and the Moon here are not to scale, but this is still, it's bigger than the Earth-Moon distance. Like, this is enormous. And this interferometer will be able to detect supermassive black holes merging at the very earliest times in the universe. And so this will be launched in the year 2034. So we have a while to wait. We have launched one of these called the LISA Pathfinder, just to check, does the engineering and does the physics like all work out? Does it do what we expect it to do? And it does. It worked better than they even thought it would. So one of these up in space can do the right thing. But to add more of them is much more complicated. And the European Space Agency is funding this and decided that 2034 would be a good year. If we get NASA to buy in, which I think they will, we can maybe push it up a little bit. So that is the future of gravitational waves. So why should you care about gravitational waves? Because for the first time, we can get information from the universe that isn't from light. We have relied on telescopes and light for every single thing that we know about space. Everything comes from light, until now. Now, for the first time, we can see things that are completely dark. We don't know if these black holes, when they merged, emitted light or not, because we don't know where they came from. Like everyone, we told observatories, we were like, there's a detection of gravitational waves over there. And everyone was like, we didn't see anything, because we didn't really know where to tell them to look. But that'll get better with time. But even some events that have no light involved, we could never know anything about them before. They were nothing to us. But now, we can know about them. There's another way to get information from the universe. This is a whole new frontier of science. We are on the edge of a new way to discover things about our universe. We've only just taken the first tiny step. Even though Einstein started to take that step 100 years ago, we are finally now there and ready to learn about these things. And it's really cool. That's what I got. Thank you very much. Are there any questions?
The floor is open. I'll try to alternate left and right.